Alright, so let's continue some of our discussion here of alkyne reactions, and we're going to talk about catalytic hydrogenation to form alkanes. We'll see there's three different reagents that we can use to do this, and really there's only one that's going to be kind of different from the things that we've seen so far. So the first thing that we can do here is we can add H2, right, with a catalyst. So this is similar to hydrogenation of an alkene. So here's your alkyne, right? If you add one equivalent, that's like a 1-to-1 molar ratio, you form an alkene. Now it's important to note that this reaction cannot be stopped here. So this is just like scratch paper theory stuff, right? And then if you added a second equivalent, it would go to form an alkane, right? So in theory, that's kind of what happens. But in reality, it goes from the alkyne directly to the alkane. So you can't stop it or isolate the alkene. That one's pretty easy because we can build that off of our previous knowledge of hydrogenation. Well, what about the next one? So what if we want to stop it? What if we want to stop it at the alkene? How could we do that? Well, it turns out if we could just make our catalyst less effective, right? If we could just slow it down a little bit, then we might be able to turn out to stop this at an alkene. It turns out that we can do that. So we use barium sulfate coated with palladium and poisoned with quinoline. So poisoned here means that the palladium is rendered less effective. The way that we typically write that down below, when you look at the overall kind of reaction, you see H2, palladium, barium sulfate, solvent here, methanol, quinoline down here below. That's a lot to remember. I usually just tell my students, hey, if we can just remember that's Lindlar's, we're good to go. So the reaction is similar to what we saw for hydrogenation of alkene, is we get cis in the end, right? So regiochemistry here, and our stereochemistry turns out to be cis on that thing, right? We get a cis addition. And the reaction just stops here. So just make a note, reaction stops at our alkene. Okay, so that ends up giving us a cis alkene. So just to reiterate what we've seen so far, we can take an alkyne and go all the way to an alkane, right? That's just with H2 and a catalyst, palladium or something. Or we can use Lindlar's and take the alkyne to the cis alkene. So the next thing to look at is how we might form the trans alkene. So the trans alkene reaction's a little bit different than the things we've seen so far. This one's the last reaction I think that we're going to see this semester that involves a radical. So this reaction involves NaNH3. Notice here that this is Na solid. So it's solid sodium and ammonium, or ammonia. So what happens is that in solution, that NH3, and let's look at it down below, that NH3 in solution, which is a liquid, you add this thing to sodium, you end up getting a sodium ion plus this weird thing, and it's a weird way of writing this, but we call this solvated electrons. So we write that by writing NH3 and a dot E minus. So you've seen those dots before, I think, when you talked about like hydrated, like, you know, metal compounds, copper sulfate, hydrates and stuff like that. So this thing is a solvated electron. Now, those electrons then are involved in this reaction. So let's take a look here down below, and let's look at the reaction. So let's take here the following alkyne. So to that, we're going to add NH3, right, dot E minus. So in this case, I'm just going to write E minus. You got your single electron here. Now, single electrons, remember, are going to use this little fishhook arrow, right? So what's going to happen here is that the single electron is going to come over and grab a hold of one of these carbon atoms. As we do that, we can't leave the atom as it is, because then it would have 9 electrons around it, right? It already has 8. So then a set of electrons now is going to come over and live on carbon. So this reaction is doubly weird because it's a radical, which is somewhat rare, and it mixes our arrows up, right? So you have a full arrowhead and a fishhook. So you get both varieties in there. Now here's the thing. You're going to get a single electron on this atom and a lone pair on that atom. But those electrons want to be as far away from each other as they can, and trans is as far away as they can be from each other. So the final arrangement of this thing has our carbon atoms just like so. In our R group, there's your radical, and there's your lone pair. So trans gives these the farthest distance away from each other possible. Now, we're going to still finish up this reaction. So we have our nitrogen, right? Because remember, we have, in this reaction, we have NH3 present, right? So what we're going to do is we're going to grab an H from that. So we're going to come over, get an H. That's going to give us an H atom on there. Still have our double bond. And then we have our R group here, right, and a single electron there. And now all we're going to do is we're going to kind of repeat that electron addition. So one more, and then we'll grab another H from ammonia. So you get NH2 minus, and an H will be added to this guy. So there's your negative charge, and then I'm going to try and squeeze this in here. All right, so we're going to come around, grab an H, and then that gives us our final product. So final product has our H, carbon, and another H here. And those H's are trans to each other here. Right, so cis is Lindlar's, and trans is the solvated ammonium. And then you get your R groups are still hanging out there. So those are the kind of coming along for the ride, so to speak.